Hello, and welcome to example 1.4.18. We are going to solve the second-order constant coefficient non-homogeneous initial value problem, f double prime plus 3f prime plus 2f equals 4x, with initial conditions f of 0 equals 4 and f prime of 0 equals 2. And we are going to solve it with the method of variation of parameters, although you will see next week, as perhaps you know already, that undetermined coefficients can also work here. The first thing we'll do is solve the homogeneous problem f double prime plus 3f prime plus 2f equals 0. The characteristic polynomial is lambda squared plus 3 lambda plus 2. And we look at that for a moment, and it factors as lambda plus 1 times lambda plus 2. And then we get our roots as lambda equals minus 2 and minus 1. So a fundamental solution set for this homogeneous problem is j1 of x equals e to the minus x, and j2 of x equals e to the minus 2x. And now we're going to prepare to solve the non-homogeneous problem. First, let's calculate the Wronskian determinant. We have w on j1, j2 at x is the determinant of the matrix whose first column is j1 of x, j1 prime of x, and whose second column is j2 of x, j2 prime of x. So that's the determinant of e to the minus x, then below its derivative minus e to the minus x, and in the second column e to the minus 2x, and then minus 2e to the minus 2x. So we calculate that determinant as minus 2e to the minus 3x minus e to the minus 3x, and we're left with minus e to the minus 3x. So now we have our Wronskian determinant, and we can begin to calculate some integrals for variation of parameters. First, we'll integrate j1 of x times the left-hand side 4x over the Wronskian w on j1, j2 at x. And so this is the integral 4x e to the minus x divided by minus e to the minus 3x. And that turns into minus 4 times x e to the minus 2x. Now this is something you do with integration by parts, and the answer turns out to be minus 2x minus 1 e to the 2x. And for these integrals, we are not putting a constant of integration on the indefinite integrals. It wouldn't add anything useful to our solution. The next integral we have to calculate is j2 on x times 4x, divided again by the Wronskian. So that's the integral 4x e to the minus 2x over minus e to the minus 3x, and that's minus 4x e to the x. Another integration by parts turns that into minus 4 times x minus 1 e to the x. Now, we are not adding a plus c constant of integration here in either of these indefinite integrals. Normally you have to do that in calculus, but here it would just add more homogeneous solutions. And you'll note I didn't actually show the integration. In order to give you interesting problems, sometimes I have to give integrals that have integration by parts in them, or something more obvious or less obvious than a u substitution. When you're doing homework or the practice problems, anything you're submitting to me, it's fine to use a computer algebra system. Just say, here I used Maple, or here I used Wolfram Alpha, or MATLAB, or whatever. And when it comes time for exams, I will make sure the indefinite integrals are very easy to do, or if I have to make them hard to make the problem worthwhile, I'll just tell you the indefinite integral. We should not be worrying about indefinite integration in this course. Okay, back to the method of variation of parameters. We have our two auxiliary integrals calculated. So a particular solution is going to be minus j1 times minus 4x minus 1 e to the x, plus j2 times minus 2x minus 1 e to the 2x. Remember, it's always minus j1 of x times the integral involving j2, plus j2 times the integral involving j1. And if you plug in the values e to the minus x for j1 and e to the minus 2x for j2, you can grind out what f of x is. It turns out to be, somewhat underwhelmingly, 2x minus 3. So 2x minus 3 solves the non-homogeneous problem. That's something you can check very easily just doing derivatives and adding. And then the general solution to our non-homogeneous problem I add in scalar multiples of solutions to the homogeneous problem, our general solution is f of x equals c1 j1 of x plus c2 j2 of x plus the particular solution 2x minus 3. So that is c1 e to the minus x plus c2 e to the minus 2x plus 2x minus 3. So I'm almost done. I just have to find the values of c1 and c2, and for that I'll incorporate the initial conditions. I want my solution f of x equals c1 e to the minus x plus c2 e to the minus 2x plus 2x minus 3 to satisfy f of 0 equals 4 and f prime of 0 equals 2. So first I'll differentiate, as I like to do. First of all, f prime of x is going to be minus c1 e to the minus x minus 2c2 e to the minus 2x plus 2. And then I want 4 to be equal to f of 0, so that's c1 e to the minus 0 plus c2 e to the minus 2 times 0 plus 2 times 0 minus 3. And that just becomes c1 plus c2 minus 3. And I want 2 equal to f prime of 0, so that's minus c1 e to the minus 0 minus 2c2 e to the minus 2 times 0 plus 2, and that's minus c1 minus 2c2 plus 2. So my coefficients c1 and c2 satisfy, as always, a linear system. c1 plus c2 minus 3 equals 4, and minus c1 minus 2c2 plus 2 equals 2. And then you have to go forth and solve this. And maybe you do it via direct substitution, or you turn it into a matrix and invert the matrix, whatever works for you. Again, on exams, on time things, the arithmetic will be easy. You get c1 equals 14 and c2 equals minus 7. So our solution to the initial value problem is f of x equals 14 e to the minus x minus 7 e to the minus 2x plus 2x minus 3. And of course, you can and should go back and check this by checking against the initial conditions and checking the actual derivatives. I often find, as I've said before, a good first test is just to plug in and do the arithmetic with the initial conditions, and if something's wrong there, then you know something's wrong even with the derivatives. But sometimes checking the derivatives can be more work. But always check your work.